Thank you everyone for being with us. This is Dr. Sam Hancock of Emerald Planet, the Emerald Planet TV of Washington, D.C. A few years ago, we met the principals of Parjana Distribution, talking about their incredible new technology that uses no external energy, but uses the heft, the heave, the flow of the earth itself to capture, process, store, and create new water from stormwater and groundwater, as it's called in many areas of the United States. So there's a very interesting seminar following this. Thank you for being with us on this webinar. And I'm going to turn it over to Lahani, if you please introduce yourself, and then they'll be able to see what Parjana Distribution is all about, some of its great projects. And we're here as a third-party evaluator, as we are television, and we're always looking for the best practices across the entire globe, and we think Parjana is certainly one of those. So Lohani, if you'll introduce yourself, give us a short overview of what we're going to be learning about EGRPs today, and we'll take it from there.
Hi, Dr. Sam. My name is Lohane, and I am a design engineer at Parjana. My bachelor is in mechanical engineering at the Federal University of Goiás in Brazil, with emphasis in renewable and sustainable solutions at the University of Cincinnati in Ohio. In today's webinar, we will talk about Parjana's presence in the US, what we do, and how the energy passive groundwater recharge product improves infiltration in the soil. In the sequence, we will see 9 successful jobs across the country, and leading to a takeaway with our CEO, Joe Kramer, and finally, a Q&A section.
That sounds absolutely great. Parjana is a Detroit-based company. Why Detroit?
We are proud to be a Detroit-based company, not only because we call it home, but because we are in the middle of the largest inland body of water of the planet, which is the Great Lakes. We are grateful to be surrounded by and to be partners with such accredited institutions like Lawrence Tech University, Eastern Michigan University, University of Michigan, and also Michigan State University.
That's absolutely wonderful. What is a EGRP? And how are EGRP applications in other states similar to maybe the applications in Michigan?
So EGRPs, as I just mentioned, is what we call the energy passive groundwater recharge product. And they are devices that help to infiltrate water in the ground. Across the country, the applications are sometimes similar to Michigan, and sometimes they're not. Each location has very particular geologic and weather aspects. You can see that we are a heavy presence in Michigan, where the soils has usually a lot of clay and groundwater is very shallow. Different from that in California, for example, we have encountered hard pans and silty clays, and groundwater there is significantly deeper than what we see in Michigan. Across this board, we have dealt with all sorts of soil types, from A to D type soils. We've literally crossed rock, gravel, and water. And one of the biggest advantages of the EGRP system is the ability to adapt and succeed in all of these different circumstances.
Thank you, Lohani, for sharing about the differences among the various states and localities where you're actually applying this technology. So let's go over, what does Parjana do in all of these different states with the various soil types, weather conditions, and climatic zones? Give us some comparisons, if you will.
Parjana offers water infiltration solutions for a variety of clients, including residential, commercial, municipalities, and agriculture applications. The nature of the challenge will change from place to place, but the solution is the same, which is to promote quicker infiltration. By quickly infiltrating water in the ground, Parjana can address issues like standing water and flooding. We can infiltrate the water locally and reduce or even eliminate the need to treat storm water, for example. Parjana EGRP system can also increase groundwater recharge, retrofit retention and detention basins, and also reduce footprint requirements for stormwater management basins. Aside from that, the system can be easily combined to other LID technologies like bioswales, permeable pavers, or even underground storage tanks.
How does Parjana ensure quality, and how do you succeed in all these diverse projects, different states and climatic zones to ensure success for all of your clients?
Well, there are things that we do before, during, and after installation that are fundamental to ensure the quality of our solutions. For example, before installing the devices, we need to analyze the site specifications and then determine the quantity and the layout of devices needed to suffice the water demand. After that, a machine that has been tailor-made to install the EGRPs will drill an average of 1 hole per minute in clay soils, only removing a little bit of material from the earth, as you can see in this circle. The installer then pushes the EGRP into the ground 2 feet below the surface. Then they backfill the hole with the soil that was removed from it. And finally, after installation, results are shown immediately. For most applications, no additional steps are required. The only exception to that is the installation at the bottom of large reservoirs when the site needs to be visually inspected. For large applications, Parjana also offered the option to monitor the site and report the system performance.
After the EGRP devices are installed, how do these actually promote quicker infiltration, and do these need to climatize themselves to the local soils, the quality and velocity of water, possibly even the temperatures of these local communities?
So to answer that question, I have here some old images that always come in handy. In the 2 pictures at the lower bottom, we have a representation of soil layers in the earth. When water moves in the earth, lateral movement within a layer takes less effort than vertical movement between 2 layers. Water molecules need a lot of energy to move from one layer to another. The picture on the left represents the water movement without the EGRP. Water can take a long time to get to that point, depending on the constitution of each of those layers. In the picture to the right, we can see what the water movement in Earth looks like with the EGRP. The device offers for water a path of least resistance between the layers. It's like an information system in the ground, telling water molecules where to move. After the devices are installed, gravity brings water down. Adhesion and cohesion forces draw the water close to the EGRP, and pressure differential will make the water move laterally away from the devices, preferring the layers of higher hydraulic conductivity. The animation on top of this slide is a representation of water movement within and between soil layers with and without the EGRP devices. And this is how the energy-passive groundwater recharge product facilitates vertical and horizontal movement of soil in the ground.
Thank you, Lohani, for your expert overview of Parjana distribution and the EGRPs for these participants to fully understand your proven technologies before learning about a number of the diverse projects and applications you're actively involved in across the United States. So let's move into some of these projects. Looking at Belle. So Lohani, what is the first project you wish to share with our viewers, and why did you select Belle?
All right, we are going to start with Belle because it's a great representation of what Parjana can do for poorly drained sites. The project was installed on Shelter 5, which has 23 of the 985 acres of the Isle. The shelter is the little blue rectangle in this picture.
So Lohani, can you tell us where the testing procedures were during this study?
Yes. Just before seeing that, I will give you a little bit more background. I will tell you the issue that they were having. What was happening is that the amount of storm water being discharged into the waste system was way too high. The total cost of stormwater management in the Isle would be as high as $1.5 million per year. So funded by a grant, Parjana took the challenge to infiltrate the stormwater before it would actually reach the system. A third-party consulting company, ECT, was responsible for this study that we are about to share. The way they set up the study was they put flow meters in strategic locations of the stormwater sewer, both at shelter 5 and also shelter 4, which was taken as the control site right across the shelter number 5. Then ECT measured the flow rates caused by rain events before and after the installation of the EGRP devices, and these are the results.
So Lohani, it looks like you also have some water quality samples taken from the sites.
We do. I will share you right after I share the results with you. In this graph, we are comparing orange lines that refer to the test site and also green lines that represent the control site. A solid line shows the cumulative flow in the storm water, and a dashed line represents the cumulative rainfall in the site. The first section of the graph depicts the site prior to the system installation. You can see that cumulative flow in the sewer system was a lot higher than the cumulative rain in the site. That led us to think that part of the storm system was collecting water from a much bigger area than just shelter 5. The same is true for shelter 4 in a smaller scale. What we see in the second part of the graph is a period after installation when the devices are not yet fully acclimated to the soil. It is visible that cumulative flow in the storm system is now smaller than the total rain in the area, which means that the difference between the lines was infiltrated by the EGRPs. Now, the third part shows the system response after the devices are acclimated. There is even a bigger difference between the amount of rain and the total amount of water in the sewer system. When looking at the control site, we can see that now the storm system only captures the amount of rain in that area, which means that the EGRP infiltrated has absorbed that difference. But also note that 100% of what rains in the control test is collected by the waste system, whereas in the EGRP site, the storm system only collects a proportion of the total amount of rain in that site. And according to the study, none of the tested water quality parameters were significantly different from the control site. In addition to that, I also have groundwater levels to share. Here we can see groundwater level for both test and control site in purple and green respectively. We can also see precipitation bars in the top of the graph and also the Detroit River depicted in dark blue. Note that both green and purple lines have approximately the same behavior before and after the installation period. During the installation, between the months of May and June and July, we can see big spikes in the water level because of drilling activity that happened to cross the water table. But please note that the levels recover to baseline after a little time. Another point that caught my attention was a big rain event that happened in August. We can see that the EGRP reacts almost immediately to the rain event, whereas the control site takes a little longer to respond to it. What is happening there is quick water recharge. The EGRP system quickly informs the path to the water table, and the water then takes its natural course. Take note of that big rain in the graph because I have pictures to show you. And these pictures were taken after that rainstorm that we just saw in the graph. The top one is shelter 4, which is a control site located right across the test site. And the lower picture is the test site with the EGRPs. I believe the pictures speak for themselves, right?
These are many excellent ideas here, Lohani. Please highlight the points you just made for ease of our viewers' understanding before we move on to the next project.
Of course. After testing Parjana performance, EST observed no standing water at the test site. There was no measurable impact on the water quality of the affected groundwater, Smaller storms no longer contributed to stormwater runoff from the test site. The groundwater elevation was not negatively impacted by the EGRP installation. The total runoff measured in the storm sewers exiting the test area was reduced by 80%. And finally, the test area became better drained, thereby reducing the saturated soils. And this completes our Belle presentation.
What a great summary, Lohani. Thank you very much. Where are we
Thank you.
going next?
So next we are going to California. Parjana was hired to increase infiltration in one of the 23 basins of a recharge facility. The picture shows the project basin in orange by the top here. Just for reference, the basin has 4 acres of area. It's over 10 feet deep, and it can hold approximately 7 million gallons of water. This facility has critical importance because about 500,000 people who live in the area depend on groundwater to sustain life. With all of that people using groundwater, its levels have been lowering more and more over the years, therefore the challenge to recharge. We were very excited to be able to work towards such a noble cause.
What results have Parjana found at the California testing site?
So the water levels at the basin they were monitored since 2011. Based on those water level readings before the installation of the EGRPs, the basin used to infiltrate daily a little under 14,000 gallons per day. After the devices were installed, that number have increased to a little over 95,000 gallons a day, an increase of over 6 times the baseline infiltration. If you look at the upper graph, you can see that evaporation, depicted in brown, was 4 times as high as the infiltration before the devices were installed, sometimes even higher. After installation, the basin started to infiltrate a lot more water than it would evaporate. Note that the lower graph, the daily infiltration in green, and observe how those numbers have increased after the system installation in 2018.
What are the advantages of infiltrating more water in this case, Lohani? It seems like infiltration is a major finding, most important to every community in the United States.
Well, first, one of the advantages of infiltrating water is that water infiltrated is water not evaporated. Every drop counts when we talk about water supply for over 500,000 people. Second, when water infiltrates quicker, more water can be added to the basin. By doing that, you're able to recharge more water per acre-feet of land in a given period of time. And another advantage, not related to infiltration specifically, is the fact that the basin needs less maintenance. No more scraping bottoms, nor adding sand to it. The EGRPs have been performing very well at this desilting basin.
The results in California are of tremendous benefits to the site's environment generally, and new water creation specifically in this great agricultural producing state. What is the next project we will see and learn about?
So the next project will be about a parking lot in Michigan, and Zena will be the one telling you that story.
Hi, Zena. Can you tell us a little bit about this project and why select a parking lot as a sample site?
Hi, Dr. Sam. This is a Parjana project at LTU, which is located in a mixed residential commercial portion of Oakland County in southeastern Michigan, approximately 15 miles northwest of Detroit. LTU was having standard water issues in parking lot D. They could not use the lot during heavy rainstorm because the area was flooded. LTU is leading a collaboration between industry partners. The project features the implementation of innovative and scalable integrated drainage design. This design significantly mitigates polluted parking lot stormwater runoff. Parjana was one of these innovative partners working to improve infiltration and decrease urban runoff, as well as reduce flooding without having negative effects on groundwater levels and groundwater quality. Another goal is to balance soil moisture.
Well, it sounds like there's many advantages here. Please tell us about the project setup and then why of this type of setup for EGRPs.
Sure, yeah. The integrated drainage system includes three separate patented technologies, including permeable pavement surface to allow parking and underground engineered soil storage reservoir for volume storage, and our innovative drainage technology to improve infiltration. Installation was completed in January 2016, removing a 20 feet by 25 feet section of the existing parking lot around a catch basin and excavation of soil to a depth of 6 feet. The catch basin was mounted as an overflow structure, and the EGRP were installed via drilling around the entire perimeter of the reservoir. In the lower picture, you can see 2 of the 14 monitoring wells dug at the site.
Why were these monitoring devices placed at the site, Zena?
They were placed there to monitor performance data like movement of water through and around the EGRP, and also the system influence on soil moisture, infiltration, and groundwater level.
And Zena, what dramatic results did you find through this extensive real-time monitoring system?
Yeah, first I'll talk about the water quality. We tested 7 parameters and TDS shown here is one of them. TDS means total dissolved solids, measured in milligram per liter. I picked this one because it represents how the values used to be high and how we have diluted in the present days, showing that the EGRP do not have negative effects on the water quality.
Zena, do you have other results you want to share at this time?
Absolutely. I have these 2 figures to show you the influence of the EGRP system in groundwater direction and moisture content. In 2015, flow direction was moving from the control site towards the center of the reservoir. There was no moisture content data reported at that point. From 2016 through 2019, the average flow direction of the shallow wells started to revolve around each EGRP. Aside from that, I have results for moisture content. In 2016, the magnitude at 1 foot and 3 feet at the control side was greater than reservoir values at the same depth. At 5 foot, volumetric water content at the reservoir was greater than at the control. That means that at the control side, only the top layer were being saturated, indicating no vertical movement, while at the reservoir, saturation was higher at a deeper level. 3 years later, the system continues to improve performance. At 5 feet, both the reservoir and the control show similar moisture content, which indicates both sides are in balance.
Zena, please share again, what does EGRP mean and how does EGRP provide this moisture content balance in the soil?
Sure. The EGRP means the energy passive groundwater recharge product, and it moves water vertically and horizontally, increasing wetted surface area between the saturated soil and the unsaturated zone. The devices redistribute water, making unbalanced moisture areas become balanced areas.
So based on what you just shared, Zena, did the project meet, possibly even exceed its purposes?
Yes, and the parking lot now is available for use during and after storm, as the pictures show. There was no negative effect on groundwater quality or level. Moisture was redistributed amongst the soil layers. And this is the end of this presentation. Now, Lohani will talk about a residential job.
Yes, welcome back, Lohani. It's very interesting that we're now talking about residential areas since we've been talking about parks and commercial areas, even agricultural locations. So share with our viewers about this quite typical residential project, which is so important to homeowners in tens of millions of residential locations around the United States.
Sure, I will actually show you two residential applications. This homeowner had issues for 37 years before he came across Parjana. Water seepage and runoff used to intrude his basement, causing a lot of inconvenience. After we installed the devices there, the basement has been dry and there's no standing water in the lawn. He stated the system performed beyond his expectations. This is how Parjana could improve this homeowner everyday life. We gave him peace of mind and no more mess to clean.
Well,
And over here is the other residential job. This homeowner used to pump water out of his backyard because it used to be flooded for weeks. After we installed the devices, the homeowner said he was very pleased with Parjana. We made his backyard available to use again.
whole thing about it, we're talking about inconvenience and the mess that it creates, but also it increases the cost of just maintaining a home and having a quality residential place to live. So it's the cost certainly is a factor in all of this. And that leads us into the condominium project in Georgia. It seems like that EGRPs are important for larger scale residential projects such as these condominiums. Please share about this large condominium project in Georgia, and why is this an excellent example for other areas of the United States?
Yes, we have here a new development area in Georgia, as you can see by the brown area in the top picture. Water used to puddle behind those houses for weeks, right here in this area where it's marked in blue. In 2017, we installed Parjana EGRPs and also set up a mini observation station with a camera and a staff gauge for reference. The system was designed to infiltrate 1 inch of rainfall in 24 hours. The lower pictures, time-lapse, show 1.06 inches of rain infiltrating within 24 hours. And the animation to the right shows consecutive rain events in December of 2018. A total of 5.56 inches of rain were infiltrated in less than 5 days after that first event. And this is a common situation not only in Georgia, but in many other places of the United States. And this is how this job is heavily connected to other applications in the US.
Looking at golf courses, it seems there are major water issues at golf courses across the United States and even around the globe. Yet these are typically wide open spaces. How does your Parjana EGRP work at golf courses?
We work very well. What was happening here is that the administration was having standing water issues in almost 1.5 acres of this course. After trying different solutions, the club president was very pleased and impressed with the quality of the results that only costed a fraction of the price of traditional methods, and as an added bonus, required no additional maintenance. So I believe that's what you're looking for when you have one of those fields, right?
Yeah, that's absolutely correct. Baseball fields, of course, there's soccer, football, baseball, softball, field hockey, many other sports, and they all operate out in open sports fields. These are really ideal as carbon sumps, something that we really need as we're facing severe climate change and increase in the velocity of rainstorms, what they're now calling cloud bombs. How does Parjana EGRP systems turn these into ideal stormwater capture, processing, and storage sites, as well as carbon sumps?
One of the benefits of the EGRP installation is that we do not compromise the use of land. Golf courses, soccer field, baseball fields, they are all regular clients. And we have also done several jobs in parks and recreational areas. So now not only you have an area that can be used for recreation, you also have area that can infiltrate water. This baseball field over here used to experience chronic flooding. The bad conditions were even captured in satellite imagery, as you can see on the top images. After the EGRP installation in 2012, the field would drain and be ready for practice even after major storms. The pictures on the bottom show the field 12 hours after 2 inches of rain, ready for practice.
Looking at roads, this is one of the most viewed, yet overlooked sites for stormwater capture, processing, and storage. These areas are major highways, local roads, and even country lanes. Why are these so overlooked while hiding in plain sight for tens of millions of Americans and thousands of elected officials?
I don't know, Dr. Sam. Parjana is here to help them do better for society now. What we're seeing here is a road application in California. The road used to accumulate water after most rain events above 0.3 inches. After installing the devices, we also set up a mini observation station with a camera. In the lower pictures, we can see the site drying after 1.25 inches of rain. And on top of that, visual inspection is showing that the trees near the system are looking healthier. Their leaves take longer to fall, and they show a fuller foliage cover, which is a great indicator that our devices are very friendly to the environment. And that is what I had to share for today.
Well, I think it's fantastic. And going back to one last note on the roads, we need to be using these roadways for different types of foliage and actually even for forestry products. And because there's millions of acres that are set aside and not being adequately used. This is Joe Kramer coming up. He's the CEO of Parjana Distribution. Joe, welcome to the conversation. Why don't you give us a little recap of the major points have been made about Parjana, and then we'll open it up to see if there's questions from our listening audience.
Hello, Dr. Sam. We've had a long relationship with you and appreciate your time, all the time that you spend with us. And thank you for participating in all of these webinars that we've had, this one and the past two that we've had over this past year.
Certainly my pleasure.
As you can see on the screen, we've have four different categories in which we're able to create massive results. In agriculture, three different areas which infiltration can be beneficial to the agricultural industry. One, healthy soils. We hear a lot about healthy soils lately. And what we're able to do is balance the moisture content of the soil. When creating that balance, we're able to manage the saturation point, available water, and wilting point in which we can help influence the farmer's yield. Second, farmland is unusable due to extended stay of water on the surface after large rain events. We're actually able to infiltrate that quicker and reduce that burn from the rain and or excessive water sitting on top. Third, the massive scale of farmlands in which we can use that runoff for recharge. And then going over to the residential, although a small portion of the business, we can actually help each individual. And if you start looking at stormwater and how we can start benefiting that, the more we can take down in a small localized area, the smaller the overall amount is that municipalities have to deal with. So on small scale, infiltrating small standing water in the lowest point of the backyard can be very useful. One, for that homeowner and also the municipality. On a larger scale, condos, apartment complexes, we can reduce or eliminate the need for extensive gray infrastructure, and then turn that unusable area into usable space. If then you look at municipalities and commercial, somewhat both of them play hand in hand together. Numerous applications were just explained to you by Zena and Lahaini on how to create a systems approach solution. We at Parjana are always looking for ways to make other BMPs more successful. With a system approach, we can break down the first flush, manage volume hold. The EGRP creates the volume reduction. The EGRP can add volume reduction and infiltration to all existing bioretention, retention, detention, or infiltration ponds. With everything you've just learned about the EGRP, the most exciting aspect from my point of view is the ability to create future water credits. So with that, we're going to open it up for questions and answers. So if anybody wants to go down to the bottom of the screen under Q&A and send in any questions they
Hi,
have.
Joe. I already have a few questions here. I'm going to read the question from Sebastian Uloa, and he's asking, does the EPA consider this to be injection wells?
Actually, no, the EPA considers this a class 5 well. If you're looking at an injection well where 2 feet below the soil, has a cap on the device, and there is no direct water connecting from the surface down through the EGRP, we create more of an infiltration on a horizontal than a vertical plane.
I have another question here from Sweta Patel. How can we fix flat street, which causes ponding, occurs in curb and gutter?
Well, you saw the one picture of the road in California where you had ponding water on the side of the road. That was actually designed for a 1-inch storm in 24 hours. And it has now been in existence for about 2 years. And we're able to infiltrate that 1 inch in 24 hours on a consistent basis. The other, as we have spoke about the systems approach, you're looking at a lot of different aspects where you could have water coming down a curb cut, go into a pretext unit. And by the way, this whole explanation is on our second webinar, which is urban infiltration, where water goes in, we take out the sediment, goes through a medium focal point, breaks down the first flush, goes into a reservoir, our tank, and then we're volume reduction on the outside of that. Again, that's small scale. We can go 5 feet by 25 foot area and manage the water off of a curb cut and or expand that to any size.
Thank you, Joe. Brian has 3 questions here. I believe we're going to start at the first one. He's asking, what is the expected life of the system? His following questions are, is there a base cost? And is there a money-back guarantee?
Well, on all 3 of those questions, the first one was
life expectancy.
Life expectancy of the EGRP. There was a study completed by Michigan Tech, and they basically gave the product a 150-year plus. On that, the only drawback on it was UV, and the UV, once it's in the ground, is no longer a situation. For us, it's more of a logistics on storage and delivery to the site. As far as a warranty, there is a 25-year warranty with a 10-year performance. And you asked the question, is there a money-back guarantee? No, there is not.
Is there a base cost?
Base costs, we're looking at $9.20 a foot.
Sebastian is also asking, how do you size the system?
That's a great question. Each site is site specific, so there are a lot of different parameters that go into that design. Area of influence, climate, soil type, all of those are taken in consideration, volume of the water to be infiltrated, and what storm effect, if it's a 1-inch storm in 24 hours versus 72, all of those parameters are taken into design.
Thank you, Joe. I have another question here from Scott Gurnall. From a permitting standpoint, what has been your experience with regulations?
With the new technology, it's always tough. What we do is look at each case individually, each municipality, what are they looking for, and then what we do is we open up a discussion with them, thinking California was going to actually be the hardest. We've actually have gone through a lot of municipalities in California. 1, they need to infiltrate. 2, it's following the SGMA Act, Sustainable Groundwater Management Act. So again, they're looking for new technologies to help promote their policies.
Thank you, Joe. I have one more question. Peter Graves, how does the EGRP handle sites with a high water table?
As you heard in the earlier conversation on the Belle project, where Lahaini had a lot of the data and went through that data, that was actually designed to reduce volume reduction on the shelter 5 in Belle, and what we were able to do is reduce it by 82.9%, and the groundwater table there was at 6 feet.
Thank you, Joe. Adam is asking, does underground or infiltrated silt eventually intrude into the EGRP and decrease its effectiveness over time?
If you're comparing this to like the silt that builds up in drain tile and then eventually clogs it, the answer is no. Again, you're 2 to 3 feet below the surface. There is a cap on it. So the earth is doing the natural filtering of the water, and the water is actually moving. Water molecules are moving from soil particle to soil particle. And what that is doing is reducing, again, going back to water quality, and the silt is going to be filtered out either through the bioswale at the top, the retention basin, the grass, whatever the surface is, the silt is going to be eliminated there. If it's not being eliminated, hence the explanation I gave of the curb cut, where you have a pretext unit that's breaking down, catching all the sediment and the garbage and everything. So we're using, again, the systems approach to eliminate issues that are typically occurring with water management systems.
And if I may just complement your answer, Joe, when we install the EGRPs, when we mention like those augers and that they make holes that are very tight fit in the ground with the EGRPs, the soil is actually expected to collapse around the EGRP. So there is no empty hole where the water comes from the top of the device to the bottom. The water goes through each molecule of water. So again, it's not a drain, so clogging is not quite a problem that we are looking to face, because we become a part of the integrated soil matrix. So yes, there are no holes and therefore no clogging. And I have one more question here from Tammy. Has your product been used in LA or Orange County in California?
It has not been installed in LA, Orange County. We're up through the Central Valley and then up into Stanislaus County and coming back down. We have a couple of potential projects in San Diego and that surrounding area.
So I have one more question, and that will be our last question, Joe. After that, Dr. Sam will take over. Can the system benefit a city that has high water table and floods during high tide?
Well, interesting. I mean, the interesting question. The portion about the high water table was actually answered with the Belle Isle. If you need more information on that, we can do a site evaluation and tell you exactly what would occur there. As far as high tide, it's like any system. It's going to be designed for certain criteria. So if we have a volume of water that's equivalent to X, then, and we design for that, if you exceed that, it's still going to infiltrate it, but what's going to change is your function of time. So we're still going to infiltrate it. If it's not in a 24-hour period or a 72-hour period, it's going to take longer to infiltrate, just like Lahaini was showing on the Georgia project, where we had back-to-back
storms.
storms. And we were designed on that project for a 1-inch storm. It just took more time to infiltrate that larger storm.
Thank you, Joe. Dr. Sam?
Thank you very much, and thank you to all the listeners to this very important discussion, because stormwater and groundwater capture, processing, and storage, and then of course turning it into new water, is a topic that's coming up to local government and even homeowners across the United States and around the globe. So what you're doing at Parjana, Joe, Lohani, and everyone there is critically important. You really are on the leading edge of this technology and the way of capturing the water and turning it into something very useful as new water. And so we've enjoyed having you on the Emerald Planet TV, and people can go there as well to look at a number of the different interviews that we've conducted over these years. So thank you to everyone for being with us. Look forward to joining us in the next webinar, and best wishes for a most joyous 2020 and a decade of the 2020s.